All right, in 9.5 part 1, we talked about this NCR notation, and we talked about Pascal's triangle. Now we're finally getting to the binomial theorem. So you might notice what I was saying about binomials in the first part of this video. When you have a plus b to the n, whatever that is, a plus b to the 5, let's say, the x term starts at n, whatever it is, and then it decreases. It goes down by 1. So if it was 5, x to the 5, x to the 4, then 3, then 2, then 1. So it keeps on going down. The first term. The second term keeps on increasing. It starts off with a to the 0, which is 1, so you can't see it. Then it's a to the 1. For the jth term, it's a to the j. For the last term, it's a to the n. So you'll see how these patterns fit when you see them as patterns. But, all right, a fairly formal, well, extremely formal way of expressing something called the binomial theorem. Running low on power here. Hold on. All right, I'm back. I just had to plug in my camera or charge my camera. All right. So we had just gotten over the very formal expression of Pascal's triangle. We've seen sigma notation before. You're really not going to use this formal notation right here, but you do need to know the nuts and bolts of the binomial theorem. All right. So they gave us a nice example of this. I suppose it's a nice example. It's x plus 3 to the 6th. And according to the binomial theorem, that's going to be, let's go back up to here. If I were to add a row to this, it would be 6, 0, 6, 1, 2, 3, 4, 5, and 6. All right, these are part of the binomial theorem. They're this 6c0, 6c1, 2, then it would end with 6c6. They're the coefficients, or at least the starting coefficients of Pascal's triangle, or of the binomial theorem. So basically, if you have a 6 there, expect to see 6c0. All of these entries from that formulaic view of Pascal's triangle. But these formulas aren't really what we want. What we really want are these numbers over here. So let me see if I can do that as well with my list. So hopefully you recognize the 1, 6, 15, 20, 15, 6, 1 from Pascal's triangle. I'm going to literally take that and to try to explain why I want Pascal's triangle. I'm just taking all of those numbers. They are the coefficients that you see here, the 1, 6, 15, 20, 15, 6. They are these numbers here in the NCR parentheses. You literally see them in this formula. I mean, exactly those numbers. So having Pascal's triangle at the ready will give you all of the coefficients that start off this form. We'll give you all of these values here through here. Now, what's the rest of this? Well, the rest of it's patterns. What happens to the x? It starts off as 6 and goes 5, 4, 3, 2, 1, 0. What happens to the 3? It starts off with 0 and it goes 1, 2, 3, 4, 5, 6. If you put those three patterns together, the pattern of the numbers given by Pascal's triangle, the pattern of the first term starting at 6 and going downhill, and the pattern of the second term starting at 0 and going up. That's it. Those three patterns. Put it together and you'll have this list, and do some calculations with the numbers, like 15 times 81. And you'll even get the actual calculations, actual numbers. So we've come a long way. This takes a little bit of work to really kind of extract all the patterns, but just so you see how it works again, let's look at something that you might be asked to do. All right. So the first term on this one is 3y, and that's going to undergo a series. It's going to undergo its own pattern. Of course, 3y to the fourth, because it starts off at the fourth power. The next term is going to have 3y cubed, squared, 1, and 0. Of course, 3y to the 0 is 1, so it's going to be invisible. 3y to the 1, 3y to the 2. So this is that 4, 3, 2, 1, 0 pattern that you've seen certainly outside of this class, is the pattern you need to put on the first term. And on the second term, -2, and by the way, it's -2 because they rewrote the expression with a plus sign in it. That's a nice way to look at it. So what the second term increases. So it goes 0, 1, 2, 3, 4. I like to do these, pull these out and look at them separately, because I've never met a student, never, over the age of 5 years old, who doesn't know this pattern, 0, 1, 2, 3, 4. Now, why does it stop at 4? Because it was a 4 here. So this individual pattern is a pattern we all know. How about the pattern for the 3y? Well, it starts at 4 and counts down. Most people know that pattern as well. If this had been an 8, it would have been 3y to the 8, 7, 6, and just would have counted down from there. So, a little hard to see when all the patterns are mashed together like they do in the book, but here it is. All right, well, let's start with the 3y's. The 3y to the 4, 3, 2, 1, and 3y to the 0 is not even listed because it was 1. How about the second term, the -2? Well, -2 to the 0, which is 1, so you don't see it. -2 to the 1, -2 to the 2, -2 to the 3, -2 to the 4. And then Pascal's triangle, those entries in Pascal's triangle taken as, well, grabbed from this side of Pascal's triangle, but calculated using this side of Pascal's triangle. So you actually see, at least in this particular expansion, the 4C0, 4C1, 4C2, 4C3, 4C4, but we know those numbers better as 1, 4, 6, 4, 1. So this is just putting all of those patterns together, and you get the results. So keep in mind what result this is. This is the result of this thing multiplied 4 times. 3y minus 2, 3y minus 2, 3y minus 2, and 3y minus 2. If we wanted to really find out what is that all multiplied together and put in its polynomial form, yeah, I'd have 3y times 3y times 3y times 3y. So of course I would have 81y to the fourth. I'd have this minus 2 times minus 2 times minus 2 times minus 2 in the last term. But these middle terms took a little bit of work to figure those out. No matter how you would multiply something like this out, you would need to really understand. You'd need to work pretty hard to do it any other way. And using patterns is definitely always the safest way. I'm just going to say, use the patterns, emphasize this formula essentially we're using here, so you can see how the result comes about. All right, now in practice, Pascal's triangle, with Pascal's triangle, you really never need a Pascal's triangle. I'd say bigger than 7. In fact, 1, 7. I haven't even made a 7 in so long. These numbers feel awkward to me, just writing it out. If you're making a Pascal's triangle bigger than 7, you're doing the problem wrong, or at least you're doing the problem the way it wasn't designed to be done. I'm not saying that, all problems will be a plus b to the 4. No, there might be a problem with a plus b to the 8, or even a plus b to the 10. But there's this wall, a difference, where the author will most likely, when it's a plus b to the 4th, ask you for all of the terms. And if you want all of the terms, use Pascal's triangle. If you just want one of the terms, and this is just this little kind of a unspoken agreement that the author creates here. If you want one of the, if the author gives you something bigger than a plus b to the 7, a plus b to the 7 seems to be the border of the website and everything. If it's a plus b to the 8 or a plus b to the 10, they're only going to ask for one term. And if they only ask for one term, you don't need Pascal's triangle to go that far down. You don't need Pascal's triangle to do a plus b to the 10. Because what are the coefficients for a plus b to the 10? They're 10C0, 10C1, 10C2, 10C3. Let's say I just wanted one term, and I knew for whatever reason, after doing my analysis, that the coefficient was 10C3. Well, that's going to be 10 factorial over 3 factorial times 7 factorial. 10, 8, 10, 9, 8, 7 factorial. Oh, let's see, cancel the 3. Looks like I'm going to get 240. Yeah. I certainly wouldn't want to make Pascal's triangle up to 10 for any reason. I mean, for any reason. But I wouldn't want to make Pascal's triangle to 10 just to find this one value. And that's what all they're going to ask. They're just going to ask for one value rather than all the values. And that little magic kind of changes around n equals 7. where they do that. All right. So just to summarize, see how this was x plus 3 to the 6th. When it's 7 or lower, they might ask for every term in the list. So all what is it, 7 terms in a plus b to the 6th. Here was an a plus b to the 4th. Yeah, every term. So where are we getting? Oh, look what happened. Now it's essentially a plus b to the 9th. You do not want to make Pascal's triangle because, well, I'll tell you what's coming. What's coming is they only want you to find the coefficient of one term. The coefficient of y to the 8th. So we start the expansion. It's 9c0, 9c1. It starts off 3y to the 9 and then 3y to the 8. And hold on, that's the term we're looking for. Anything beyond that, just a waste of your ink. You don't need to go any further. This is the only one they want. Do I build Pascal's triangle to calculate this term? Let's hope not. I know this one, 9c1, is, well, it's just 9 from a rule we had earlier, which they didn't really showcase very well, but all right. So it's 9 times 3 to the 8 times 2 y to the 8. That's the entire term. This was 9, 3 to the 8, put the, times 2. All right. And they just want to know the coefficient. So they drop the y in this from here to here. Usually when they use equal signs, I really kind of wish they had left it in. Y. All right. But the answer to the question is, what is the coefficient? And they are correct. The coefficient is just this number from that 1 to that 8. How do we calculate it? Well, with a calculator. By the way, we could have used the NCR calculation, or we could have used one of our rules. Remember, I don't know if you remember, but one of our rules was NC1 is equal to N. So 9C1 is equal to 9. That's kind of a freebie. Again, we didn't know it was 9C9 until we did a little bit of work, but hopefully you see the major difference is when they have a larger number here, they're only going to ask you for one term. All right. I almost laugh when I see this particular formula. I would never recommend someone trying to use this formula. I mean, it goes against pretty much everything I like to talk about, making visible things or invisible things visible. It's not wrong. They're saying that if you have ax plus b to the n, so let's do an example. Well, let's look at an example here. If you have 3x or x plus 3 to the 10th, and they're asking you to find the term containing x to the 7. Well, this formula will give that to you. That's not what they did. Fortunately for us, that's not what they did. But and you say, oh well, what's the term containing x to the 7? Now I'm going to say using this formula is just a bad idea, but it would work. N is 10, J is 7. We could work it out, but I would much prefer you just kind of expand this. 10, 0. In other words, make it visible. X to the 10 plus 10c1, x to the 9, and then don't forget 3 to the 1. 10. I'm going to get there. X to the 7. Not this term, but the next term. 10 C3 x to the 7 3 cubed. So this is the term. I didn't even know which term it was. Turns out it was not the first, second, third. It was the fourth term. I got that. But how would I calculate this? Well, of course, 3 to the 3 is 27. You'd calculate 10C3, multiply them together. Hopefully you get the idea. Did I use this formula? Not once. In fact, I've never used that formula. So make the list and then just calculate what you have, which fortunately for us, that's what the author did here. So this was a different question. This one didn't ask you for what turned out to be the fourth term. I didn't know it was going to be the fourth term because remember I was saying I was looking for the term that had x to the 7 in it. Well, they asked very directly, what's the fifth term? Again, they're just going to ask one. Oh, yeah, what's the fifth term? Expand it until you get to the fifth term. First, second, third, fourth. The fifth term is right here. And then you calculate that. Couldn't be clearer. I highly recommend this method. They did say method 2. So solution A. What's solution B? It's to use that weird formula. So the formula was, first of all, they had to figure out that you wanted to find the term that contains x to the 6th. How do you figure that out? Well, the fifth term would go through this pattern, x to the 10. What was the question? X plus 3 to the 10. So x goes from 10, 9, 8, 7, 6. So first, second, third, fourth. There's the fifth term. So since I know I'm looking for the term that contains x to the 6th, I can put n here, 6 there, n is 10, this 10. The formula had all of this. A to the n minus j, I think it had in the formula. So you can see it, and you get there. You get the same answer, but you really are keeping visible things invisible with this, and I'm not really a fan of this formula. You can probably hear it in my presentation. I've quite literally never used that formula because you could just make the list and calculate actual numbers. This is just a weird way of saying this is how Pascal's triangle is built. I don't think you need to know this, but what I'm saying is let's put some numbers in here. If this were, say, 8C3, and this were 8C4, and that's exactly how it would look in Pascal's triangle. This would be a term. This would be the term that followed it, and this would be the term underneath. What term is that? Well, the next row down, it's one more than the 8s, so that would increase. And this would be the fourth term in this list. That might be a little harder to see, but this is just telling you how the Pascal's triangle is formed. You're not asked to do anything with it. So that is kind of bringing us back to this NCR. The only thing I want to leave you with is I definitely recommend you not just do the NCR calculations by hand. That's pretty much all I've done here. When I had 10C3, I did it by hand here. This time it wouldn't be top factorial, but 10 factorial divided by 3 factorial divided by the difference factorial, even if I wrote it this way. But know how your calculator does this, because we're going to see this formula again, this NCR again in another section. Actually, in that section, another section of the book, they might write it this way. But in any case, know how to use your calculator to do the NCRs, not just Pascal's triangle or just the expansion by hand. And that'll serve us well in the future. The other thing is, be able to do Pascal's triangle and get a complete list of numbers that way. All right, that is 9.5. See you in the next video.